Hi, it's Caitlin from the Ocean Tracking Network. In this course, Kim Whoriskey, PhD candidate in statistics at Dalhousie University, will walk you through a 3-point checklist for choosing an analysis for your acoustic telemetry data. By the end of this session, you'll understand the roles that goals, response variables, and method plans play into the choice of statistical analysis for your data. This course is part of an acoustic telemetry workshop series and includes examples that will help you along the way. If you'd like a copy of Kim's PowerPoint presentation, you can download it using the link in the description.
Today, I'm just going to try and give you a brief introduction into how we might go about analyzing our aquatic telemetry data, which is kind of a big and lengthy topic, because there are so many different kinds of statistical techniques out there that we can use. I have decided to kind of group it into 3 different statistical concepts, which we can always come back to, or 3 different things that are important to our analysis, which are the goal of our study, the response variable that we're looking to analyze, and also the actual method. So I'm going to try to relate it back to those 3 concepts in an effort to help us organize all of this information in my brain. So we're all here because we're studying aquatic telemetry. I'm just going to talk briefly about the differences between satellite and acoustic telemetry. So here I get to work on both of these. I'm very blessed to do that. On the top, we have an example of a tagged seal, and I just really like showing my seals. On the bottom, we have an example of a tagged fish. When we're looking at satellite telemetry data, we typically sample the animal wherever it's going. So we really get this spatially continuous estimate of a path, basically. Whereas when we're working with acoustic telemetry data, we're typically only getting detections, we're getting estimates of locations wherever the receivers have been deployed. And we can then go into we can try to estimate spatially continuous data from that, and we'll come back to that at the end of the talk. But those are the 2 main differences that we see right from the beginning. And so for the purpose of this talk, we're mostly going to be focusing on these spatially discrete detection data. Before we get really into it, I just do want to talk a little bit about the challenges with detections and analyzing detection data, just so that we keep these in the back of our minds. And the reason I like to talk about this right from the beginning is because I didn't really sit down and think about it until recently, but it is quite a unique system, and statistically it's quite fun to take on. So just to start off, we do have spatially discrete data, right? So we're only sampling wherever we put out these receivers, and that actually means that we have an inherent bias in our data. So because we're only sampling those animals wherever our receivers are, if we're not careful with where we place our receivers, we might not get a representative sample of whatever we want to test for our hypotheses. So in something like this, here's a lake in Denmark where my friend Henrik Backtoft has been tagging some pike, and here we have pretty extensive coverage. And so here we feel, I'm pretty sure that we would have a fairly unbiased sample of locations of the animal and of the different environments that the animal might encounter. But in other cases, if you were only in, for example, coral reefs, and you didn't get any of the deep water, then you would be able to only talk about your animal and its behavior within those coral reefs. So we do have this inherent bias. Whenever we collect detections, we're really only measuring the presence of an animal. Sometimes we actually miss that just based on our detection efficiency. I think probably most people here know about that, so I won't go super into it. And we have to infer absence. And so we have to think about, okay, if we have a lack of detections, was the animal actually gone or was it not? And all of that relates to our detection efficiency. And the detection efficiency itself can vary in time and space. And so that means that the meaning of a presence, so the meaning of our data, the actual definition of it, is dynamic over time. And that's because these detection ranges are changing. And so, yeah, that's just a really, really interesting problem that I like to think about. When you have overlapping receiver ranges, like in this example here, it means that a single data unit can actually lead to multiple observations. So we get a lack of independence in our observations. So we tend to think about this as pseudo-replication, and we tend to think about it typically with when we have multiple observations on an individual, for example, and you have to incorporate ID as a random effect in a GLM, but you can actually get pseudo-replication just in the data themselves, so within an individual as well. Oftentimes, if you have overlapping detection ranges, you've done that specifically to use an analysis that actually uses that, but if you don't and you have overlapping detection ranges, that's something that you can have. And then finally, you can have collisions that lead to false detections. And I'll admit that was actually something that I didn't really buy into. I didn't think it was probabilistically that easy for that to occur, but it definitely is. I have my friend Rob Lennox, who's been mentioned multiple times. He's been in the field and he's had a lot of false detection problems with some of his studies recently. And so here are those three kinds of recurring themes that I mentioned in the beginning that I wanted to organize all of our information in when it comes to statistics. And so we're going to talk today about the goal, which is really the point of your study. So it's, what do I want to know about my animal? We're going to talk about the response variable, which is the what you calculate from your data. It's the thing that you're going to analyze. And finally, we're going to talk about the method, which is probably what everybody here is for. It's really the kind of statistics that you want to use for your data. But all of these things are interlinked. And I really wish that I could tell you that it was an easy relationship and that the goal really easily leads to the response variable. So you come up with your goal, and then because of that, you know what, you go out and collect your data and you calculate your response variable, and then you know exactly what method to do. And so you get this nice linear relationship, but it's actually, in my experience, statistics, it has not been like that at all. So the relationships look a little bit more like this. So especially for me, somebody who's doing their PhD in statistics, I often go backwards. So I'm focusing on the method. I'm coming up with the method that leads me to figure out how to calculate my response variable. And then I can figure out, well, how is this applicable to ecological systems? But also just kind of, as you're going through a study, you're going to be adjusting your method and your response variable and your goals kind of back and forth a little bit. Try not to adjust our goal, because that means you're adjusting your hypotheses tests, and that can lead to some biases and some problems in your significance later on. But other than that, all of these are really going to influence each other. And furthermore, there's going to be lots of other things that are going to influence your choice of statistical method and how you conduct a statistical analysis. So, for example, we have the study design, whether we're in a linear system like a river, or whether we have extensive coverage like in that lake that where Henrik has been tagging fish, or if you're in the open ocean, like with a lot of the OTN receiver gates out there, for example, the Halifax line. We have assumptions of the methods. These are really important, and sometimes our data set will violate these assumptions, and so we'll have to adjust our method. You have computational power. Sometimes it's hard to figure out. Sometimes some methods can be computationally infeasible to do, and unless you're somebody like John who knows how to put their computer in parallel, I'm not like that. I don't know how to do that yet, and so it can rule out some methods right from the get-go. You have different covariates that can affect what kind of method. You have data loss and gaps. I've heard of people who've had their laptops stolen, so they've lost data that way. You also just have gaps in it from our measuring devices, so from our tags. Autocorrelation, space and time can cause different methods to be more useful or not. And then finally, there's also personal and co-author preference. And that's a totally normal thing to rely on too, right? Because you're probably, if you're more familiar with a method, you're probably going to be better at using that method than with other methods, at least at the beginning. So yeah, it's not super easy to do statistics, but this is I think that boiling it down into these three core concepts is a good place to start. And it is kind of a linear relationship in time, right? So I will come up with a goal first, ideally, and then I will go out and collect my data and calculate some response variable from it. And then I will apply a method to that to evaluate my goal or my hypothesis. So just to go over these quickly, I've kind of already talked about them, but the goal is really what you want to know about your animal. So there's lots of different things that we can ask with telemetry data. These are a couple of different options. I won't go too into it, but we can look at habitat distribution. We can look at timings. We can look at behaviors, niche partitioning. You can look at social dynamics, different ecological events like spawning. There's lots of different stuff. So it really, the goal is going to frame the rest of the analysis. And hopefully you're already going to have this because it's included in the whole grant writing process. So it should all be figured out, I guess, from the beginning. It's also going to automatically eliminate some possible methods just just based on your study design and things like that. And it's going to set up the infrastructure for inference and hypotheses tests. So whatever you want to actually formally test statistically. And then we go into the response variable and detection data. We're pretty lucky. They're very versatile. So we can calculate a lot of different things from these, anything from presence and absence to counts of individuals or residency indices. And we can calculate these kinds of data over both time and space. So at each of these different receivers for within each month, for example, I can look at the number of individuals that were detected. So it really, the response variable is a series of numbers that represents the animal behavior that we're interested in looking at. And you use these numbers to test hypotheses about your animals. And the response will need to take on a specific structure for your chosen model. And then we get on to the method, or what a lot of people will probably think of as their model. Unfortunately, there is no one-size-fits-all method. I would probably be out of a job if there was. Some methods will be better suited, however, for specific combinations of goals and response variables. So this is one way that the method can actually go back and kind of help you tweak your response variable. In reality, many methods can be used to achieve a single goal. And so that kind of redundancy can, I think, seem annoying a little bit at first, but it's actually a really powerful tool for testing hypotheses, because it means that if we can test an ecological theory with multiple methods and we come up with the same answer with multiple methods, we're going to be more sure that our conclusions are correct, or that we're going to have more evidence that we're going to have more evidence supporting our conclusions. And one other thing I like to talk about too, just to make people aware of this, is that in addition, a lot of branches of statistics can be related to one another if you delve deep enough. And so that means that to some extent, names in statistics become a little bit redundant, and they kind of lack meaning to some extent. Because, for example, I've heard a lot of people talk about how hidden Markov models are specific cases of state space models. I've heard other people say state space models are special cases of hidden Markov models. I've also heard people talk about hidden Markov models as unsupervised classification techniques, which is sort of like machine learning. So there's just a lot of different relationships in there. And so I just like to give I like to give people warning about this so that they don't get bogged down in names. And so if you really just do your reading on statistics, and if you do your reading on your method, I think that's enough for our purposes. But yeah, so basically the method is a suite of statistical rules that you can use to test your ecological hypotheses. And what's really important is that it always comes with assumptions that need to be checked. So some methods that we'll just briefly go over: we have generalized model survival analysis, Mark-recapture analysis, network analysis, a little bit of machine learning, really just random forest, and some triangulation methods. So in generalized models, the goal is really to estimate the association, and it's an association between variables, so your response variable and other covariates, and you want to look at the significance of those different associations or relationships. And so your response variable in this case, you might be interested in looking at home ranges, presence, absence, distance traveled. GLMs are really the most easily applied statistical technique out there, because they're very well documented and they're very flexible. You can incorporate additive relationships, not just linear ones, and you can incorporate random effects and autocorrelation terms. The sky is basically your limit. That might be a little bit of a stretch, but they're very, very powerful tools, obviously. Here's an example of a generalized model. This data set here comes out of a study that was a 2-year-long study in the Kinbasket Reservoir, British Columbia, where bull trout were tagged and their movements were monitored within the lake. And so in this study here, Lee-Gutowski looked at the interactive effects of sex and body size on their movement ecology. So their goal was really to quantify the movement patterns over seasons and between sexes, and also over size. And so in their instance, the response variables included home ranges and total displacement. Here's a typical GLM table. It shows you the significance and the values of different covariates and the coefficients associated with the GLM. And here we can see the home range sizes as predicted through the GLM over the different seasons. And so you can see that there was a significantly higher home range in both spring and fall compared to summer and winter. Moving on to survival analysis, the goal here is really to determine the factors that are significantly associated with an important ecological event. So we're actually looking at specific events that we are assuming that we can measure, something like migrating out of a river for the first time, or being trapped through a dam. And the response variable is the time that it took for the event to occur. So you could just analyze these data with a GLM, with a logistic regression, and use a 0 for the event not occurring and a 1 for the event occurring. But when you use survival analysis, you incorporate the time that it took for that event to occur, and that gives you a little bit more information. Here's an example of a survival analysis, the same study system, but a different paper, one done by Eduardo Martins, where the goal was to determine whether season is associated with bull trout dam entrainment. So the response was actually the time to the entrainment. So this bull trout being unintentionally passed through the dam. And so the response here is actually plotted on the x-axis instead of the y-axis, which is what we're normally used to looking at. And then on the y-axis, we have the percent of fish that became cumulatively entrained. So we see here that we don't have we don't have an increase in entrainment. It's all static throughout, for example, 2011, spring, summer, and fall. But then as soon as we get to fall, we have an increase. And then especially over winter, we have an increase. So it looks here like we have an increased probability of becoming entrained in the winter. Here's another example of survival analysis. This is a pretty cool paper that came out recently by Alex Filous. I hope I pronounced that name right. He studies, in this study, he was studying yellowfin tuna in the Republic of Palau. And the way that basically in Palau, they are trying to start up a yellowfin, and they're trying to grow their yellowfin tuna industry, fishing industry, to help support local subsistence and economy. And the way that they try to organize tuna fisheries is through something called a fish aggregating device, or a FAD, which is this kind of moored buoy with plastic ribbons on it that attract fish to it so that fishermen can go and more reliably fish the tuna. And so the goal in this study, in part of this study, was to quantify the difference in retention time within the FAD network between young of year and year one tuna. So 2 different age classes of tuna, and looking at how long they stayed within the FAD network. And so the response here was the time that it took for a tuna to leave the FAD network. And so here on the y-axis, we again have the time. So we have our response. And then on the x-axis, we have, this time we're going down in the number of fish. So it's down in percentage of fish that were leaving the FAD network. So we see here, for example, we were very static between 50 and 120 days. No fish really left for age 1 years. And then we all of a sudden see a drop again. And you see a marked difference in the age 1 and the young of year ages. Okay, moving on to Mark-recapture analysis, and I really wish I could spend more time on this one, but I really can't. The goal, it can be used for a variety of things, but often it's used to estimate population dynamics classically, or we can look at movement. So for example, we can look at population size or survival, especially, and it's really especially useful when you want to account for detection efficiency issues. And the reason it's useful is because it models the probability of detecting an individual, but it actually splits that probability into 2. It splits it into the probability that your animal survives from a previous time to your next time, and then the probability at that next time that you can actually see it. So it's a way of accounting for the detection efficiency that we have in acoustic telemetry. The response period itself in Mark-recapture is a series of zeros and ones. So it's a 0 here denoting absence, which again we infer, and then a 1 denoting presence. Here's an example of Mark-recapture, and it doesn't really give a very good plot, but it gives us a nice table where, and this is an example in a paper that I wrote with Eduardo and Lee and a couple other people, including Rob, and we looked at our goal of this study was to estimate the survival and probability of detection of bull trout within that Kinbasket reservoir. So it's that same study system. We did this just for a single month, just January. We looked at multiple different covariates, whether sex and length and time influenced this. We found that none of them really influenced it. The best model was just a static model that had the probability of detection and probability of bull trout, or probability of detection and probability of observing our bull trout, or of them living. Anyways, and the character strings are literally, again, zeros and ones, denoting absence and presence. So the data actually looks like this. So one thing that I'd really like to note in Mark-recapture is that it is a time series model, so it has to be discrete in time. Network analysis, this has gotten pretty popular over the last decade or so. The goal here is to assess the connectivity of a system, either receivers or animals or both. The response constitutes these adjacency matrices, which describe something called an edge among your nodes. It's the edges, which are the relationships among your nodes. And so we've already taken a little bit of a look at that today, so I won't go much into it, but this is basically what your response looks like. But most packages will actually calculate that for you, I believe. Here's a quick example of network analysis, again, in that the bull trout Kinbasket reservoir study, where we were trying to see which areas are important for bull trout. The nodes here constitute receivers, and they're weighted here by the degree, which is the number of incoming and outgoing edges of a node. So we can see that this receiver here, for example, is really connected to the other receiver, so it's probably pretty important. And then you have your edges weighted by the number of movements. So thicker edges mean more animals moved. And then back in Alex Filous's paper, we have, he had a really good example of a bipartite graph. So his goal was to assess the connectivity of tuna with the individual fish aggregating devices. So he had nodes that constituted the animals themselves, which are the circles, and then the fish aggregating devices and receivers, which are the rectangles here. And so that's what we call a bipartite graph. And what we can see here is that this receiver here was very important. It had the highest degree. And you also see a decent amount of segregation amongst your animals here. So these different colors represent different age classes. We see that they're not really interacting all that much. And then I just wanted to take a quick look at machine learning because I found a really cool paper yesterday that talked about it. The goal here is to classify data into groups. So it's not, typically when you're using machine learning, you're not as interested, I would say that you're not as interested in the relationships that force the classification. You're more just interested in, can we predict whether this animal was part of this group or a part of that group? So the response is the group, but it's also kind of the model. And these groups can include, for example, whether you're looking at predation, so your animal was predated versus not predated, or looking at out-migrants versus non-migrants. But technically, model input when you're doing this includes things like movement metrics, age, length, sex, etc., whatever you can use to split your animals into these different groups. And so in this paper, this came out of the Atlantic Salmon Federation, where they were studying stripers and Atlantic salmon smolts. They had movement tracks of the stripers and they had movement tracks of the salmon smolts. And they're worried that the stripers might be predating on the salmon smolts. And so what they were interested in doing is trying to see if the smolts were being predated upon by the stripers by assessing their movement tracks and comparing smolts that had an unknown fate to smolts that had a known fate. And so their goal was to classify these tagged smolt movement data into either predated or not predated. And the response variable consisted of 8 movement metrics from both known fate smolts, known fate bass, and unknown fate smolt data. So here, for example, they had a striped bass movement track, and here they had a smolt, but that was classified by their algorithm as probably having been predated upon because it looked a lot more like a bass than it did like a smolt. Here they have an example of a smolt that was classified as a smolt track because it didn't look that much like a bass. And here they had an example of a smolt that was classified as another bass. So I just thought that was a really cool paper and a really innovative way to look at predation. And then finally, we'll just go quickly over triangulation. And that's a way of trying to get our detection data into a more fine scale estimate of an animal path. And so really what we're trying to do is estimate or predict this underlying animal path, but your response variable is your raw detection data. And there are lots of different methods that you can use. So you can use FEMCO positioning system, you can use center of activities, which we've also heard about, or you can use YAPS, which is yet another positioning solver. And that's a state space model that Henrik Backtoft has created. And the important thing about triangulation the important thing about it is that it opens up a whole other suite of tools that can be used to study animal ecology. And that might include things like hidden Markov models, resource selection functions, home range analyses. It really opens a lot of different tools. And so if you can get these more fine scale data paths, then you can do a lot of other different things, which constitute an entirely different lecture. And with that, I'd just like to say thank you to my co-authors. This presentation was built off the building blocks of a paper that I wrote with all of these fantastic people. And thank you all for having me.
Thanks for watching the Ocean Tracking Network on YouTube. If you enjoyed this presentation, there's a good chance you'll like some of the other videos in this series. Click on the link in the description below for the workshop playlist, where you can learn more about the R programming language and some R packages suitable for exploring and plotting acoustic telemetry data. Keep up to date with our latest videos by tapping the subscribe button or clicking over on this list to see more workshops in this series.